Today we're going to be taking a look at molecular geometry, or how molecules look in 3 dimensions. The way we can predict the geometry for molecules is VSEPR theory, or valence, shell, electron, pair, repulsion, which basically says that the repulsion between electrons causes electrons to be arranged as far away from each other as they possibly can be. So if you keep in mind electrons want to be far apart from each other, that's going to give us patterns in the 3-dimensional geometry for molecules. As far as what the shapes will be, the easiest rule is if it's diatomic, meaning if it's made of 2 atoms, it will be linear, because the only way you can connect 2 atoms is by a straight line. All other molecules can have different shapes based on the steric number of that central atom. A steric number is the total number of bonds or lone pairs around that central atom. And for counting a steric number, a double or a triple bond would count as just one thing around that atom. So for example, this would be a steric number of 4, because I've got 4 things around that central atom, 2 of them being lone pairs, 2 of them being bonds. If I had this situation instead, this would just be a steric number of 2, because I've got 2 double bonds coming off of that carbon, but it's just considered 2 things coming off the carbon. The parent geometries are then going to be the main possible shape categories, and all the shapes will either be the same as this geometry or some kind of derivative of that. So this number of electron pairs, this is the steric number. So you can have 2, 3, 4, 5, or 6 things at most coming off of a central atom. And here's pictures of, if we were building these models in 3 dimensions, what those different parent geometries would be. The way we're going to then figure out a molecular shape is first by drawing the Lewis structure. From that Lewis structure, we'll be able to find the parent geometry, which is one of these. Then we're going to picture that geometry without the lone pairs, because any lone pair is not an atom and it's not really going to show up in the shape. And keep in mind that lone pairs do take up more space than the bonding pairs do, so they can actually push things around a bit. For example, this picture you see down here is starting off with an octahedral parent geometry, because there are 6 things coming off of the center atom. The Lewis structure for this xenon tetrafluoride is 4 single bonds and 2 lone pairs coming off of that center atom. If we go back to this octahedral shape and picture 2 of these bonds, not as bonds, but just as electrons, which you don't really see, then we end up with that derivative shape, which in this case ends up being a flat square. So we're going to go through each of these steric numbers and see what kind of possible derived shapes you can get from them. So we'll kind of have them all organized in categories based on this steric number. So for steric number 2, I mean 2 things coming off of your center atom. If there's only 2 things coming off, the farthest away I can get these electrons from each other would be 180 degrees apart, which is a straight line. So any steric number 2 is going to be a straight line. So the official name of that shape is linear. For steric number 3, now we're going to have more than one possibility. If there are no lone pairs, meaning everything is a bond coming off of that center atom, then what you're going to see is the parent geometry. And here it's a trigonal planar shape. Planar meaning flat, trigonal meaning a triangle. So if you look at this in 3 dimensions, you have a totally flat triangle. If, however, I take one of these bonds to an atom off and make it a lone pair instead, as is the case here with SO2, here SO2, it has a steric number 3 because there's 2 bonds and 1 lone pair, so 3 things coming off of that center atom. The shape here is called a bent shape, and you can see it derived from this trigonal planar. If I go back here and just take one of these bonds off, and that's a lone pair instead, okay, a lone pair of electrons doesn't really show up in the shape, it's just influencing. So the actual shape that's left is this sort of V shape, which is called a bent molecule. Steric number 4, and this is probably the most common steric number because 4 things around a central atom would be a total of 8 electrons, so that's pretty common. If none of them are lone pairs, then the parent geometry of 4 things coming off your center atom is called a tetrahedral molecule. They tend to kind of look like back scratchers. It's hard to tell in this picture because they're all crunched up a little bit, but you kind of have one coming at you forward like this. These two would be in the same plane, and that one's sort of coming behind a little bit. If I take, however, one of those 3 off and make that a lone pair instead, like we have with NH3, I still have a steric number of 4, because there's still 4 things around that center atom, but one of them is electrons instead. So if I take this tetrahedral molecule, take that off, this is just electrons that you don't really see. Now I have this shape, which is called a trigonal pyramid. So the base is a triangle, but if you kind of envision it in 3 dimensions like that, you have a pyramid. I can have a second derivative shape, though. If I have 2 of these as lone pairs, then the leftover molecule is a V shape again. So this is another way of getting a bent molecule. If I go back to my tetrahedral here, if I take out this one and I take out this one, what you have left over is that V shape, which is bent. And here's an example, and this kind of shows those shapes a little bit better, I think. A tetrahedral molecule here, so this is my tetrahedral parent geometry. And you can see the bond angle is 109.5 degrees. That same angle in the same spot on an ammonia molecule is only 107, because these lone pairs right here do actually push these bonds all down closer to each other just a little bit. Water has 2 lone pairs on that central hydrogen. So if you envision taking that off, and all you have is electrons in those spots, you can see that bent shape where that comes from a little bit. And 2 pairs of electrons bends this angle down even further. Now to the expanded octets, a steric number of 5. My parent geometry here, if there's no lone pairs, just bonds, is a trigonal bipyramid. That sounds really fancy, but if we take it apart, trigonal means we've got a triangle base here in the center. Bipyramid means if we were to connect these faces, I've got a pyramid on the top pointing upwards and a pyramid on the bottom pointing downwards. If, however, I take one of those off and replace it with electrons, like you have here in this Lewis structure for SF4, so if I take this guy right here off and look at the shape that's left, if I take this left one and rotate it 90 degrees, this is the shape I end up with, and the name for that is a seesaw. If I take my steric number 5 and have 2 lone pairs instead of 1, then the leftover pieces, what you've got, is called a T-shape. And if I back up to my original bipyramid, we can see where this comes from. So here's my parent geometry, the bipyramid, and if I take 2 of these guys off, if you look at what's left, I have a big straight line and then one thing coming off of it, which would make a T-shape. Last derivative shape possible here for steric number 5, if I have 3 lone pairs on that central atom, which you can see here with this Lewis structure, 2 single bonds, 3 lone pairs around the center, then a linear shape is what I end up with. If I go back again to my bipyramid, if I take this guy off now, so all 3 things here on the center are lone pairs, all that's left is a straight line. Last steric number 6. The base parent geometry is octahedral. So if I have everything around that center atom is a bond, we have an octahedral shape. The name 8, you can see that 8 in there, and that's because if we were to connect these faces, it would be an 8-sided figure. But octahedral is the name you need to know. If we take one of those off and make it a lone pair instead, so if I scratch this guy off down here, and that's just electrons, the shape that I get as a result is a square pyramid, meaning a square base, but it's pointed up as a pyramid. There we go. If, when I draw my Lewis structure, I have 2 lone pairs on that center atom, then what's left is a square planar, meaning a flat square. So again, if I go back to my octahedral, if I take this one off, so these 2 are lone pairs, all that's left around the center here is a flat square. This picture would be taking the one that I've been drawing on here, and if you kind of rotated that towards you 90 degrees. You're looking at this from the top down now. A lot of different shapes to keep track of. Here's another way of kind of organizing the idea of keeping the parent geometry and all the derivative shapes that go with it. So this spatial geometry would be the parent geometry. This electron pair geometry, don't worry too much about right now. These kind of weird orbital looking things we will address later, so this will make sense later on. And then lone pair substitutions, meaning if you take any one of these bonds off and put electrons instead, we're looking at all the derivative shapes now. So for linear, even if I took something off, 2 is still a straight line, so that would still be linear. Trigonal planar, I can end up, if I take 1 off, with something bent. Tetrahedral, take off 1, I get a trigonal pyramid. Take off 2, and I get something bent. For the trigonal bipyramid, if I take off 1, this is calling it a sawhorse. This is the same thing I earlier called a seesaw. Both names are okay. T-shaped or linear. And then same thing with octahedral. If I take 1 off versus 2 versus 3, and it keeps on going. So just a different way of looking at the same pictures we'd just seen. All right, with all that in mind, take a moment and see if you can figure out these shapes, draw the Lewis structure, and figure out what shape you think it would be. Take a moment and give it a try. For the first one, CCl4, if we draw the Lewis structure, it's going to look like this. I've got chlorines on all 4 sides of that carbon. Each chlorine has its 3 lone pairs here around the sides, but there's nothing fancy in here. No double, triple bonds. The carbon has 4 things around it, which means the parent geometry would be tetrahedral. None of them are lone pairs, so we do stick here with the tetrahedral geometry. For the next one, HCN, when I draw this Lewis structure, I end up with a triple bond right here, and then just a lone pair on the nitrogen. There we go. So this has a steric number of 2. There's only 2 things coming off of that center carbon. One of them a single bond, one of them a double bond. So a steric number of 2, the only possible shape we have is linear. That one is going to be a straight line. The very last one, Br3-. This one you had to be really careful with, counting up all your electrons. Keep in mind that that negative charge means you do have an extra electron. And this is going to end up being one of your expanded octets. You'll line up all 3 bromines. Regular 6 electrons around each of your outside bromines. But that center one, for this to work, you ended up with 3 lone pairs around the bromine. So here I've got a steric number of 5. There's 5 things around that bromine, 2 bonds, 3 lone pairs. Steric number of 5 with 3 of them being lone pairs. This one is also a linear shape. Lots to work with, and we'll build some models of these too, so hopefully we'll have a better picture of what they really look like in 3 dimensions. You are all set.